all the, I don't know. All right. I don't want to. You know how to operate this thing?
No.
All right. I'll try this Friday, but here I'll just give you a little preview, and then Richard will take over. So this is a bimetallic strip. We have two different kinds of metal here. They have different coefficients of thermal expansion. So what do you think is going to happen? So on the top, we have something that has a relatively low coefficient of thermal expansion. On the bottom is something which has a relatively high coefficient of thermal expansion, right? So for a given change in temperature, this will expand more, this will expand less. What's going to happen if we heat this thing up?
Curl up.
Right, it's going to curl upward. That's right. And I really do want to get this thing to work, actually. I wonder what this button's for. Maybe there are directions on this thing. Oh, look at that. Oh, now we're talking. Okay, so, let's see. Oh, I must have got it backwards. Here we go. There we go. Look at that. So on the top, we have a small coefficient of expansion. On the bottom, we have a large coefficient of expansion. We heat it up, and look at that. It curls upward, right? You have to be careful when you design your next bridge. Make sure you don't design a bridge that does this when it gets hot and cold, right? And now this is a reversible process, right? We can stick the thing into water, and the process undoes itself. That's pretty cool. Ah, good. Keep going. All right, right. So you can look at that. Sizzle, sizzle, and it flattens back out, right? Okay. And here are a bunch of little things. They all have candle wax on them, and these have different thermal conductivities. Remember we said that the heat transfer per unit time goes like the thermal conductivity times the area times the temperature difference divided by the length, right? So basically, if I heat up this part here, we should see the pieces of wax melt at different times. I don't actually know which one is which here, but we're just going to heat up the bottom, and then we'll see how fast it takes the heat to conduct right down to the end. I should probably be wearing safety glasses for this. Oh, look at this. The one on my right-hand side, your left, is already starting to melt. Can you see that? Look at that. Okay, now what? Let's see. Oh, and the next one's starting to go. See, now two of them have gone. What's the difference between these two? The only difference is the thermal conductivity. I hope we don't set up a fire alarm here. See, so you design a frying pan at some point. You want to make sure you think about what the thermal conductivities are of the different pieces. One more thing here, and then we'll let Richard take over. Notice these things don't fit together, right? Well, what happens? I think they're made of the same material. What happens if I heat this one up? Oh, this is like that question. You heat up a disc with a hole in the middle, and nobody believes that the hole expands also, right? You say, no, it must expand to fill the hole. People say, no, the outside expands, maybe the inside doesn't expand. Well, let's see if the inside expands so I can fit the ball through. So we're going to heat this thing up. When we heat it up, it's going to expand, right? Pretty much everything expands when you heat it up except for water between 0 and 4 Celsius. Hey, look at that. Now, Bill Burner told me don't ever leave these strapped together when it cools back down. Real hassle for him.